Right, this is Shear, and this is going to be example 1, which is on page 8 of the notes, and it says find the distribution of shear stress in a solid rectangular section. So let's assume that we have a simply supported beam, as we always have, and then let's suppose that the force coming down is V. Let's suppose that we make a cut down there, and then that force up there is V over 2. And then let us assume that the cross section is of a shape like this. So if we do a cut at AA, that is going to be section AA. So let's now assume that that section AA has a breadth of B and a depth of D. So it's a rectangular section. So the area of the section is going to, so area, which I'll call A, is going to be B multiplied by D. So if we wanted the shear force distribution, we would call the average shear force V over 2 divided by B times D, if V is the load coming down on the beam. So let's now remove that, and let's call that 20 kilonewtons, and then down there our two reactions would be 10 kilonewtons and then 10 kilonewtons. So if we now drew, let's try and draw it in 3D. So let's draw the section where the cut is, which would be there, and then let's draw it back down to the support. So the support is there, so up at the support there would be 10 kilonewtons, which is going to be our shear force. And then down here, let's just say that we're going to have a look at it around the centroid. So that axis is going to be Y. So if we did a plot at that point there, and we had another one that's Y going up, and then down here we could call that tau, and then tau would be in newtons per millimeter squared, and then tau is obviously the shear. So simplistically speaking, one option for tau would be that area there, and that value of tau would be 10 kilonewtons divided by the area, and that would be known as tau average. So all we're saying here is that we've got a shear force of 10 kilonewtons, and if we divide that shear force of 10 by the cross-sectional area, then we would get an average value of the shear stress. And before we go further, let's say that where we make the cut, so that's going to be 10 kilonewtons, then we would have the shear force coming down of 10 kilonewtons as well. and I'm not showing the moment on that plot as well. Okay, actually, let's just show the moment there. So if that distance was say 2 meters, then the value of the moment would be 10 kilonewtons multiplied by 2 meters, which would be 20 kilonewton meters. So that would be the free body diagram. 2 meters. Okay, now so I'll put that as I'll shape that with a value there. Now, if we wanted to know the actual distribution of the shear force, so again, I'll do that plot there. The real distribution of the shear force is going to be like there, and then that value there is actually going to be tau average for a rectangular section times 1.5. So i.e. it's going to be 50% higher than tau average. So let's see how we can derive that. We'll draw our cross section out here. So I'll draw the cross section there. And of course we know that at the top surface and at the bottom surface the shear stress must be 0, so we can see that that is 0 newtons per millimeter squared, and then that value up there is 0 newtons per millimeter squared. Now let's start with the formula. So we'll start with the formula tau as a function of y is equal to V, which is the shear force. So in our example, our shear force is 10 kilonewtons, which is the same as the reaction. So from the shear force diagram we would have a value of 10 kilonewtons, multiplied by S dash, and you can see S dash is also a function of y, and divide that by I and multiply that by B, which has also been shown as being a function of y. So V is the shear force, which is, for the case of a simply supported beam, that's the same as the reaction. I is the second moment of area, so that's the second moment. We can see that B is a function of y, which means that if we had wanted to, suppose the breadth of our section could have varied going upwards, for example, but in the case of a rectangular, that is constant, and so that therefore, i.e. in the case of a rectangle, that's going to be B. So let me draw B there, which is the breadth, i.e. breadth of section for a rectangle. And then this S dash Y is the first moment of area. And in terms of Y, Y is measured from the centroid of the section. So if we have a section of breadth B and depth D, then you should know that the centroid is going to be there, which is going to be at half the depth, and that tells us that all our measurements for y would be moving up from the centroid. And if you wanted to call that axis there something, it could be either z or x. So if we assumed whatever is going along the length of the beam may be x, and maybe that could be z, but it doesn't really matter, because it won't be part of the equations for a rectangular section, although it may be part of the equations for a centroid. For a shape like that. So we have that is equal to V. Now let's suppose that we wanted the shear stress at that point. So if we wanted the shear stress at that point, and that point is a distance y up, as it is, because that's the axis. So it's a general distance y. So at that point we would draw that line there. Now, and we're going to shade it. So S dash y is the first moment of area, really about the centroid. So the first moment of area, let's sketch that out. So that's going to be d over 2, and that's going to be our distance y, which we've indicated. So just a general distance y up the y-axis. So the first moment of area is going to be b multiplied by d over 2 minus y. So the d over 2 so that distance to the centroid is going to be d over 2, and then obviously that distance there is also going to be d over 2, and so that distance there is going to be d over 2 minus y. So I hope you can see that, because that distance is d over 2 and you subtract y. So we've got b times d over 2 multiplied by y. So the whole bit there, that is actually going to be the area of shaded portion. So that needs to be multiplied by the distance to the centroid of the shaded portion. So the shaded portion, the centroid of the shaded portion is there, so we're talking about that distance. And that distance would be that distance there would be your distance y plus half of d over 2 minus y. So it's y to get up to that point, and then that distance at the top is d over 2 minus y, and then the centroid is halfway up in the shaded portion. So that's why we have y plus d over 2 minus y multiplied by half. And then at the bottom we would have the second moment of area of a rectangular section, which you should know is 1 over 12 b d cubed. So if you simplify that, well, firstly let's note, you can see that tau is indeed a function of y. And just to reiterate, we're getting that equation from our notes. So we've not derived that expression, that's come straight from our notes. So if we simplify that, that will come out as V times 3 d squared minus 4 y squared divided by 2, and then that bit there would become b d cubed. So our shear force as a function of y varies as a parabola, and let's stick a value of 0 into the expression. So if we did tau at 0, which would be 0 would be here, so tau at y is equal to 0 would be the maximum value. Tau at y equals 0 is going to be equal to the shear force times 3 over 2 d squared over b d cubed, and that would be equal to v times 3 over 2 divided by BD, and BD is going to be the area which we had up there. Therefore, you can see that the shear stress at 0 is going to be 1.5 times the average shear stress, because the average shear stress is V over BD. So tau average is equal to V over BD. And then if we substituted tau at d over 2, so up here that would be y is equal to d over 2. If we make that substitution there, we would get v, and then d over 2 times d over 2 squared, d squared over 4 times 4, the d squareds disappear, so you would get 3 over 2 d squared minus 4 d squared over 4 over bd cubed, and the 4's would disappear, the d squareds would disappear, therefore you get 0. So we can see that that shape there, that parabola there, is the distribution of the shear stress, and the shear stress starts at 0 at the top surface, and then it becomes a maximum value at the centroid of the section, and then it goes back down to 0 at the end. And if we wanted to plot the shear stresses on that shape there, we might start off with very small shear stresses, and then the biggest shear stress would be in the center, and then when you get to the end, the shear stress would be 0. So if you wanted to plot the profile of the actual shear stress, you would get a distribution like that, that being tau, and that would be, of course, being y. So the shear stress distribution in a rectangular section is parabolic, and is given by that expression.